in the file. So that if we want to get this, the operator that should remove ms equals 0 degeneracy between the degeneracy between ms0 and ms plus minus 1 should be a little bit similar to the one of the Zeeman effect, but should be square. Okay, then it should be dz square. Okay, and then of course if I have sz square acting over ms equals 0, that's of course it's for the spin. This will be for a spin s equal 1. So you have to write s equal 1. So that would be 0. Okay, so sz in that case is equal to 1, 0 minus 1. Okay, and 0 here, 0 here. Okay, and so now sz square about ms equal plus minus 1 would be plus minus 1 square ms h bar. Okay, ms equal plus minus 1. Okay, so that would be h bar ms equal plus minus 1. Okay, h bar square. Good. So there was a mistake. And then we see that the action is the same on state ms plus 1 or state ms minus 1. Okay, so now let's come back to the following. So we've been able to build, you know, the electronic state, orbital state, for each electron. And we saw that somehow now we add the spin. Each electron has a spin 1/2, so we have to fill the state. We already started doing that. But now we really want to write the state associated to that. So what we can do is we have to ensure that the overall state, the overall wave function, is antisymmetric when we consider the exchange of the two electrons. So antisymmetry can be obtained two ways. Can be obtained either by acting on the spin or acting on the electromagnetic wave function. And then if, for instance, the spin part is antisymmetric in the exchange, then regarding the orbital electronic state, those will be symmetric in the exchange of the two spin. So this is what we're going to do now. So we take, I remind you that if we have two spin state, two spin 1/2, then if we take into account, if we now add them, we'll get either spin s equals 0, that's the singlet state that we have here. Okay, that's the singlet state. Okay, and this is antisymmetric when I flip-flop, when I change the two spins. Or we have the triplet state, and the triplet states are their linear combination of the two spins, and that are symmetric in the exchange of the two spins. So this is what I can use now for that. Okay, so just a little bit different notation. Alpha and beta in this slide will be either spin up or spin down, but it was more convenient, and I reused some old slide. So what we have to do now is to have on one side the orbital state, and then we add the spin state. And this is done by this product here, okay? This tensor product here. So what we do, remind that we fill the 6 electrons, okay, of the NV minus center, and then we fill the states. The first one, A1 prime, which was the most symmetrical one regarding the orbital wave function in the structure, will be within the valence band. So somehow it's forgotten. We can forget it. The electrons are bounded to the crystal, are stuck in the crystal. Then we have the other state that are in the band gap of the diamond. And then when A1 and then the ground state, then we put 2 electrons on AX and AY. That's what I'm going to write the state this way. A1, 2, A2, okay? So now what I do now is that I add the spin state. So what I can do is take now those, what matters is those states, of course. So what I need to do is now I can have either symmetrical combination of those states, and then in that case, I will have anti-symmetrical spin state, or I can have symmetrical combination of these states, and in that case, I will have then anti-symmetrical combination of the other state. So if I now combine an anti-symmetrical function of this one, this will be ax, ay minus ay, ax, okay? And then I have three possibilities for the spin, so total, the degeneracy will be 3 for this state, and that will be plus plus, plus minus, plus minus plus, and minus minus. All those are degenerate. And we write this state in the following way, 3a2. So this is not 3 here, means that we have, it's 2j plus 1, so spin 1, so we have 3, that's the degeneracy that we have, okay? And a2 is just a notation taking into account the symmetry of the defect, not so important. The other possibility is to write now with symmetrical combination of those states, and then an anti-symmetrical combination of this state, of the spin. And that's these three possibilities. This is we have this exchange, so there should be something, there should be a mistake here. There should be a mistake here. Okay, maybe there's a mistake here. I have to think about it. But there is this combination of the state, and at the end, we reproduce now the other one. This is, okay, let me see. Oh, yeah, no, it's symmetric. No, it's symmetric because x is changed, xx, or ay. This is changed, and I found this. And the other one will be changed xx and ay. So it's symmetric. This is symmetric when I change the two states. Sorry, I'm not started my brain. Okay, I reactivate now. I should reactivate it. Okay, good. Now we do the same for the excited state. And the excited state, it's a little bit more complicated. Well, it's the same. Somehow you write down all the symmetrical wave function. Okay? So once I have that, now why is it important that we do that? I remind you, we have these two electrons. The two electrons, they will interact, of course. And they have two possibilities to interact. They can interact through dipole-dipole interaction. That's the spin of one dipole acting on the spin of one dipole. So that's a direct magnetic interaction. Okay? And then we'll consider that later. But then they have another way. They have an indirect way to interact together, which is like in the helium atom, the exchange force. When the spin are up like that or like that, depending on the symmetry of the spin state, you see that I change completely the position of the two electrons. So what does that mean? I change completely the orbital wave function. So if now, and let's remind that there is two electrons, so there is an electrostatic interaction between them. Okay? When I am in this configuration with here S equals 0 in the singlet state. In the singlet state, you see that I have a symmetrical wave function for the orbital. So if it's symmetrical, the electrons are allowed to go close to each other. And that's somehow an average value that will enhance a little bit, that will enhance significantly, sorry, not a little bit, very significantly, the Coulomb, their energy. Okay? Exactly like in the helium atom. In the helium atom, you have two parts. The helium atom associated to the spin S equal 1, and the helium atom associated to the spin s equals 0. And you find very different energy level. Okay? And it's just the consequence that there is an electrostatic interaction that is somehow modulated by the orientation, by the spin state. So in all these states that I have here, the electrons are allowed to go close to each other. And somehow the Coulomb interaction between them, since they are of same charge, will increase the energy. Whereas if now I considered the triplet state of the electron, in the triplet state of the electron, this is associated to an antisymmetric wave function for the orbital. So this is the position now of the electron. And this antisymmetric position, you can convince easily yourself that you forbid the two electrons, it is forbidden for the two electrons to be at the same place, just because it's an antisymmetric combination. Okay? So what does it mean? It means that the electrons somehow, due to the fact that it's a kind of force depending on the spin orientation. This force that the triplet state induces this exchange force on the electrons so that they move further away from each other. And that was actually discovered by Heisenberg in the 30s, who understood that and who somehow could explain, introduce this to understand the spectral properties of the helium atom. So it's exactly the same effect. So somehow that system, since the electrons are further away from each other, their Coulomb interaction is significantly decreased, and that will give me the ground state. Is it clear or not? So after that, we have to do the calculation. Of course, we have to go into the detail of the wave function and do the computation. And this is rather difficult. This is very difficult, actually. And the person that was one of the first to do it, to do that job, to be able to perform all this difficult calculation, and in the specific case of the NV Center was Marcus Doherty at Australian National University. So he played a key role. Marcus played really a key role in understanding really the structure of the defect together with Neil Manson and also other people, but I think you really deserve credit for being able to really understand the structure of the energy level. And the structure of the energy level somehow is shown here. And you have many papers from Marcus, like this one, that describe in detail this theory. But somehow you see, this is my level. I do not take this energy level. Now, if I take into account the Coulomb interaction, the Coulomb interaction will increase a little bit that level. And then what I can do, this is this ground state level. But this is also now the other level, 1A1. This is associated to a singlet state of the electron. And now the Coulomb interaction is very strong between the two electrons. So this raises the energy of this level very high. Okay? And here in between, you have the other level, which somehow depends on the structure, and it's, if I come back, it's those levels. So the Coulomb interaction is increased, but not so much as for that level. Okay? And the ordering just need to be, you need to do the calculation for finding that. And we have the same effect for now the excited state, with here, this state is associated to the triplet state, okay, and that state is associated to a singlet state, okay? So at the end, and this is what matters, and you can somehow keep that in mind, we have now two separate electronic levels, very well separated, one which will give rise to the strong red luminescence, okay, between this level, 3A2, and this level, 3A. This is how we will call them, okay, usually. And this is associated to a spin triplet S equal 1. Okay? And this is a transition, and then you have an optical transition between this level associated to a wavelength at 637 nanometers. So this is an important band that was first observed and explained and that we already discussed. And now, apart from that, you have another manifold, which is now associated to the spin singlet state, S equals 0. And this is 1A here, it's this level, and 1A1. And you can have, nevertheless, if I take into account the structure of these electronic orbitals, I have a non-zero electric dipole that can exist between those two states. I can compute that and see that if I do, for instance, 1AX, and this will be this one, and X. Sorry, it's not easy. Maybe if I do that, it will be better. That should be Y, I guess, and 1A. This will be not zero. So I can have an electric dipole moment that exists between these two transitions. I can create somehow an electron oscillation that will act as an emitting dipole of this transition. And that will be a transition at, if I now write it down, this is 637 nanometer, and this is 142 nanometer in the infrared. But those are completely decoupled, like in the helium atom, okay? You have the singlet, you have what was called the ortho-helium and the para-helium a long time ago, and it's a little bit the same. We have somehow the ortho-NV and the para-NV. That would be the para-NV, okay, where you have a spin existing, and the ortho-NV in the singlet state would be associated to the other system. At that point, those two manifolds do not interact. They are well separated, okay, and we have close transition inside them, like in the helium atom. The helium atom, when you are, for instance, in the singlet transition, you can have very, very long-living state, and it's, the metastable helium is associated to that. So if this would be somehow close to the helium atom, we would have here a metastable NV center that could survive for very, very long time until something happens that brings back to this ground state. But we will see that actually this happens much more frequently due to the interaction with the lattice. Okay. Now, I concentrate on that. In the following, I concentrate on that state, okay? And that state now, I want to explicitly look at its fine structure, taking into account now the interaction, the direct interaction between the two electrons. The direct interaction between the two electrons will be the magnetic dipole-dipole interaction. Okay. Each is a spin 1/2, meaning that one electron, the spin of one electron can create a magnetic field, and that magnetic field will act on the other spin of the spin of the other electron of the pair. Okay? So I'm trying now to do that. So you have different approach. I will use a very simple approach, step by step, to show you the degeneracy to really build the system. So again, now let us forget the orbital part. Okay, so we have the electron, it can have its transition, but forget that. We only look to the spin part. So the system now is on the basis, is described by three states, S equal 1, N equal 0, -1, or 0, or 1. And now I want to look to the degeneracy of those states. Again, what I need to understand, there is this 2 pi over 3, okay, dependence. In a rotation invariance. So when you have a system and you do an invariance on that, you can easily look the transformation, can compute how the wave function or the state will be modified by the rotation. You take this operator, R alpha, written as exponential minus E alpha, this value. You take this expression, okay? And then this is simply the influence of the rotation of the system. So if you go from initial state psi, you apply now this operator, and you would get the result, the spin after the state of the system after the rotation. And so if we now apply that operator on the state M here, then we have this very simple explanation. So what we have here, so again, the basis state are we show that they are eigenstate for these eigenvalues, 1 exponential minus alpha. So the NV center is invariant by rotation of angle 2 pi over 3 over the z-axis. So that means that we have this property. And obviously, that tells us that I can build now an Hamiltonian that has the same eigenstate as this. So that tells me that somehow the eigenvalues of my spin s equal 1 are also eigenstate of H0. This is important, okay? So I know already from that somehow the basis for Sz is a good one for H0. Okay? So I do not have to worry about trying to find other states. I just can keep these initial states, and there will be the good one. It's the good choice. Now I can also check the Hamiltonian. So the Hamiltonian, I have also the symmetry of the plane. So I remind you that we have the plane, the axis x, was chosen in a way so that there is a mirror symmetry between the symmetry of the plane xy, xz, of the NV centers. So I just take that into account. And so then it tells us that I have to introduce the parity operator as defined by changing y in minus I. So it's this, okay? And I have to see whether or not what's the influence of this operator on the basis that I have chosen. So I can do this calculation, and it's not very difficult to show that at the end we have these properties. So it means that somehow the mirror symmetry impact tells us that state s equal 1, ms plus 1, and state s equal 1, ms equal minus 1 will have the same energy. Okay? Otherwise, I will not be able to fulfill this mirror symmetry of the molecule. So just by doing that, I know already that the ms0 state will have the lowest energy. So this you can convince easily yourself by that, due to the interaction after that. And the two states will be above. So with only this argument, I can now say, this is my situation. I have ms plus minus 1 here, and ms equals 0 here. And there is certainly a difference. And the difference is only due now to the magnetic interaction between the two dipoles. And I can compute it not directly using this basis. Okay? So I do this calculation now. So I take the magnetic moments associated to the spins of the two electrons. You know how to write in electromagnetism the magnetic interaction between these two dipoles. It is given by this formula. And now I just need to change the S, which would be the associated to the magnetic dipole, into operators, and I have this explanation. Okay? Here, it's a key property at that stage also. I completely forgot any possible coupling between the electronic part of the state and the spin part. And this is due to the fact that we have no spin orbit coupling. Or it's so weak that we can neglect it at this level of approximation. Otherwise, it does not work. What I would have then to do is, like in atomic physics, you consider then the J total angular momentum as J equal L plus S, and you have to work in the new basis as defined by the spin orbit interaction. The good point is that they are completely, we forgive that. We live, spin and electronic wave function are in different Hilbert space. So now it's not difficult to do the calculation using that. And associated, you simply now use this 1 minus 1, 0. And this is a direct, very simple calculation to do. And you have here the explanation. You have here the matrix that I have. Depending on this dependence of R between the distance of the two spin, and that will give you the strength of the magnetic interaction, of course. But okay, that is another difficult issue to compute because it depends on the details. But at the end, you can also say it's an experimental parameter and try to see if it matches the computation. But people that do, for instance, ab initio calculation, they will know how to do it because they have the full distribution of the electronic density, and they can easily do such calculation. Okay, and at the end, I end with this expression. This matrix is equivalent, can be written as Hz squared minus SS plus 1 divided by 3 times a parameter d, which is defined by all that. Okay? So this is quite simple to do. And at the end, we can also rewrite that somehow. This is just the unity operator, so somehow we can forgive that. If you want, it's just a redefinition of the energy ground level somehow. But we have something which is proportional to Lz squared with a given factor before. Okay? So the level structure at the end of my NV center, if I only consider the spin property, is just a spin S equal 1, M equals 0 in the ground state, and M equals plus minus 1, separated by a frequency of about 3 gigahertz. Okay? And this is what we're going to play with now for all the following. And also remarkably, we have the same spin structure, of course, in the excited level, but with certainly a parameter d here that will be different because, of course, in the excited level, it will be smaller because usually in the excited level, the wave function are larger compared to the ground state, and the magnetic interaction will be decreased due to the extension of the wave packet somehow of the two electrons. Okay, so you can rewrite that differently. For instance, you can say I have 3 parameters, d1 sx squared plus d2 xy squared plus d3 sz squared, that you can rewrite in this way. So d sz squared minus ss plus 1 divided by 3 operator identity plus a parameter e times sx squared minus xy squared. If I have a full symmetry of the defect, then this parameter d1 and d2 will be equal, okay? And e will be equal as 0, and I have only this parameter. Okay, I have only this part of the wave function. And it's the structure I demonstrated. If now I have some parameters, some physical parameter that somehow break the symmetry between X and Y, and you can, for instance, imagine that there are some strain in the crystal that will break the symmetry between X and Y. Now, D1 can be different from D2, and then I have to take that expression. Okay? And in that case, what will happen is that somehow this will remove slightly, will mix the state ms plus minus 1, and remove their degeneracy. You can show that. And so instead of having only one resonance, I will have 2 resonance peaks with a small frequency difference that is due to the E parameter that can be, for instance, induced by strain. Okay, what we will D and E are called zero field splitting parameter. I forgot here a field. I will put it here. I cannot do it. Okay, I will do it later. Okay. Okay, zero field splitting parameters. This parameter G is due again to the magnetic interaction between the dipole. So if, for instance, I act on the lattice parameter of the diamond matrix or the diamond lattice, the two electrons might be closer or further away from each other, and I can change the D parameter. It actually what happens with if you change the temperature of the sample, of the crystal, and then what will happen in that case is that the parameter D will depend on the temperature through the lattice dependence of the temperature. The temperature dependence of the lattice, and the typical variation, D of parameter D over dt is minus 74 kilohertz per Kelvin. So if I change the temperature by 10 Kelvin, I will have something of about 1 megahertz shift of the whole spectrum of the NV center. Okay. So this is very nice because then I can use, as I will show some example later, can use NV centers to really measure the temperature. And this has been done, for instance, in living cells, where people have used NV centers in nanodiamonds. Nanodiamonds, it has been shown that they can be very easily integrated by living cells. So somehow the cell capture them, and somehow the nanodiamonds will go to different places in the cell. And just by measuring the temperature there, it's very important because then you can monitor in real time the activity of the different part of the cell, provided that something happens on the cell or whatever you want. So this has been used in life science very importantly. Now, there is always a question about possible bias in their measurements, so those experiments are quite challenging. Now, the other parameter is that E is equal to 0 if we have the perfect C3V symmetry, because X and Y play an identical role. But as soon as we have, for instance, strain applied to the sample, that will break the C3V symmetry, so that there are two directions that are not equivalent regarding the NV axis at that time, then that would create E parameter. And for instance, in CVD ground diamond, you usually have two peaks separated. The NV resonance will appear as two peaks separated by about 100 kilohertz, and that can be much larger in nanodiamonds. For NV embedded in nanodiamond, where it can reach 5 megahertz up to 20 megahertz, depending on the way the system has been fabricated. The nanodiamonds were fabricated. Okay, so I hope that now I have shown all the things, but still we have to understand one important point. The important point is how we have optical spin polarization. There's two important steps to see. First, and I should have written that, I remind you that the electronic transition occurs between electronic states that are completely decoupled from the spin states. So it's not at all like what we learned in atomic physics. In atomic physics, the spin-orbit coupling is very strong, so it binds together the spin and the orbital motion of the electron. And that allows you, and what matters is the total angular momentum, J equal L plus S. And you have learned atomic physics in this way. Here we are in a very different situation. The situation is now the spin is on one side, the electron is on the other side, and they do not speak to each other somehow. Okay? So what does it mean? It means that if you want to transfer angular momentum, you cannot, that will be not on the spin. You can change the angular momentum, the orbital angular momentum, but you cannot change the spin because there's no way for the electromagnetic wave to act on the spin directly. So the spin will be conserved in all optical transition. So that leads to a very different selection rule for the transition due to the absence of these of this coupling, of this spin-orbit coupling, the selection rule is delta M equals 0. And this is very important. You cannot change, using light absorption, the spin state. So it means that we have this spin structure, ms equals 0, ms plus minus 1 in the ground state. We have the same structure in the excited level. With different parameter, it's only 1.42 gigahertz as a frequency difference. But we keep the same structure. And now what we have are transitions that link together states that have the same ms value. So ms equals 0 will be bounded, will be connected to ms equals 0 state in the excited level. Okay? And the same for the other transition. We have the two transitions here. We cannot change ms in any absorption by light. Now, so we have this closed transition. Initially, the population, as we saw, as we did in the calculation, is just thermally distributed among all these levels. And we remind you a little bit, 3 gigahertz, it's about the frequency difference of a few, just around 0.5 Tesla for the spin of a given of an electron. If you remember, the population difference will be 10 minus 4. Okay, that I will add in relative population, the relative difference in population. So somehow I can say we have equal population here and here. So I have optical transition starting with all these levels. They are closed. So system goes, for instance, here, comes back here by decay. The decay, the radiative decay is about something like 13 nanoseconds. So I absorb light, 13 nanoseconds, I emit a photon, and I have this closed transition, and the same on the other one. And the ms state, the singlet state here, is very far in energy, so I do not populate it. Nevertheless, it can be populated through what is called an intersystem. I should write it down. Here, it's the inter-system crossing effect. There is the interaction of a phonon, and the interaction of a phonon will change the spin state. It will flip-flop one spin, okay? So, and that can occur only from those states, because this is a very symmetrical situation, if you remind. It's AX plus AY. So a flip-flop keeps me in the same state, okay? I won't, but this is very different. Now, it's a combination where if I flip-flop one spin, then I end in something which is a singlet state here. And you can convince yourself about that. So somehow I just have, by the flip-flop, I can now decay non-radiatively, just by interaction with the lattice, to the singlet state here. And once I am in the singlet state here, the system is connected to the other level, as we saw in this rule here. Okay, that structure. So now it can decay from here to here radiatively by emitting a photon at a wavelength of 1.42 nanometers. And this occurs within a time scale of 200, 300 nanoseconds. Once I am here, now I can again decay. The system can decay back again by flip-flop to those states. They are both allowed from here to here, and they repopulate that. So, on the other hand, ms equals 0 toward ms equals 0 is a closed transition. No possibility for the spin, for the NV center to go to the singlet manifold. This means that we have, if you look to that, we have exactly an optical pumping scheme. We start from the system of ms equals 0 state, we're on a closed transition. Whereas when we start from ms equals plus minus 1 state, we go to the triplet state, but from time to time we go from the singlet, and the singlet will preferentially decay to ms equals 0, and then if it decays to ms equals 0, then I'm on the closed transition. So after many cycles of these excitation, all population will end in the ms equals 0 state. You will have still some population on the singlet state, but most of the population will be on the ms equals 0 state. And so you have used this optical pumping scheme to polarize the NV into MS equals 0. So you prepare the spin state on the ground state, just for instance by shining green laser light on it, and after some time, typically some hundred of microseconds, the system will be polarized very efficiently at more than 90% into the ground level. So this is remarkable somehow because we do not need to do anything. Just apply green laser light and the system is polarized. And now, how do we detect magnetic resonance? Suppose I apply continuously a microwave signal, and I will scan its frequency across the transition between MS equals 0 and MS plus minus 1. What will happen? The system is on the closed transition, and when we are far from the resonance, it remains, there's no resonance, no Rabi oscillation between the two systems. So the system is on MS equals 0. Now, when on resonance, the NV can go, the spin can go to the MS plus minus 1 state. And how I see that on the signal? Now the signal from here, each time I start from here, absorb light and comes back, I get a photon. Now, if I look the probability of getting a photon from those states, here 1, but from time to time, I can go to the singlet state. And then the system is trapped there for a long time. So the radiative yield from the MS equal plus minus 1 will be smaller than from the MS equal 0 state. That means that this state, I can say, is very bright, whereas the state MS plus minus 1 are somehow dim, and will produce less luminescence than the other one. So just by monitoring the level of luminescence, it's just the light that is collected during a given integration time, and I use that to monitor, to compute the intensity of luminescence of the NV center, then I can really see if the NV center is on the MS equals 0 state, then I have a strong intensity of light emitted, and as soon as I flip, the system has been transferred to the MS plus minus 1 state, then I see a level of intensity that is decreased, and that's the ODMR contrast, and that's just the optical signature of the magnetic resonance. And then it's so sensitive, this detection, that compared now to what I told you regarding electron spin resonance and the standard techniques for their detection, this now we use the optics, and this can go down now, you can really play with a single spin. So you have the sensitivity using that to really look at the magnetic resonance of a single electronic spin using this technique. And this is somehow remarkable. Okay, now what we can do from that, if you want to do it, if you want to go further away, you just need now to write the different equations that will affect the systems. And then you end with a model that is rather complicated because somehow you have to take into account this excitation, the decay to the singlet state, but there are also some possibilities that the system, due to, for instance, different photon excitation, goes to the other charge state, the NV0 charge state. So when you do all that, you have a set of rate equation that allows you to compute all this transfer rate, and at the same time, you can add on them a coherent drive of those MS equals 0, MS plus minus 1 state, but described exactly like I showed you before. So somehow you need a way to, if you want to model the NV photophysics and the signal that you want to observe, you need somehow to integrate all that using this combination of rate equation, just rate that change the different system, and this coherent drive of between those states. And maybe we try to see, to do a kind of calculation using this approach. That's one approach. You can also do the complete calculation, but it will be much more difficult. It's better to simplify the situation with rate equation that tells you the population in the different states, and then you play with the coherent drive on the system. And you have some detail in those papers, in this paper, for instance, that we implemented. There's many other papers that have done similar things. Okay, why is the NV now a good magnetic sensor? So suppose now, as we say, we can have these two states. We can discriminate them by the intensity, their respective intensity level. We can prepare the system in MS equals 0 state, okay? And we can play with magnetic resonance trick. Now, if here we apply a magnetic field at first perturbation order, it will remove by Zeeman effect the degeneracy between +1 and -1, and you just have to take into account the calculation. There is a J factor here, okay, and this is what you see. Instead of having one peak, now I have two peaks, and the frequency difference that we have here is proportional with some parameters that are perfectly known, the J factor and mu b, the Bohr magneton, of proportional to the intensity, to the amplitude of the magnetic field once projected on the NV axis. So using that, you have somehow an atomic scale magnetometer, and this is what we will use, and I will show you tomorrow some applications of that technique, of sense of this dependence with magnetic field. One point which is remarkable is this value of J parameter, which was measured before using ESR experiment. And this parameter is very close to 2. And 2 is a value we get for really a spin 1/2. So why we have that? Because we do not have spin-orbit coupling. So somehow we deal with bare electrons in the system, completely somehow independent of the diamond lattice. Of course, the diamond lattice will come into the T1, T2 parameters, but their dependence with respect to the magnetic field or the microwave excitation is really 2. And that leads to a Zeeman shift of that one peak of about 28 megahertz per millitesla, or a frequency difference, which is just a double, which is what I gave. And the typical sensitivity you had just with this experiment, being able to look at the shift of a given peak about with a typical signal-to-noise ratio, and again, we will try to compute that, what is how we can compute the magnetic sensitivity. We try to estimate that by calculation, is about is in the micro-Tesla range. So with an NV center, you can, without any problem, detect a magnetic field in the micro-Tesla range, and there's a lot of work that has been done in this direction to investigate that. We published some years ago a review paper on this technique that you can see that reviews the different possible implementation of this dependence regarding a different approach. And there's also a lot of now papers that are getting out, reviewing all the work that has been done, exploiting this sensitivity of the NV center to the magnetic field. Okay, maybe I say, maybe we can stop, no? And have a tea and come back for just a few slides and then